Okay, so we're looking at problem set 8, where we're going to use Laplace transforms to solve differential equations involving discontinuities. Now what you're going to see in these problems is that we often have to sort of build up towards the differential equation. So we often have examples where we might be given some function, g of t, it's a discontinuous function. We need to express it in terms of the Heaviside function and then find its Laplace transform and then use that then to find the solution to a differential equation. So let's start off here with example 1 and I'll show you what I mean by that. So example 1 here, the beginning of this problem is a quick application of your tables. I'll leave you to solve part A here. I'm going to move right along to part B. So in part B we're given a function g of t which is given by t between 0 and 1, and it's given by 0 for values of t greater than 1. And we're going to need to find g of t in terms of the unit step function or in terms of the Heaviside function, and then find its Laplace transform. So let's take a look at that. So this is question 1, part B. So in this problem we're told that g of t is equal to t when t is between 0 and 1, and it's equal to 0 for t greater than 1. And notice there that we're not actually told what to do with the value t is equal to 1, so we're going to have to try and figure out what the most sensible thing to do is. So the first question we need to address is sketching what this thing looks like and using that sketch then to write this in terms of the Heaviside function. So let's sketch what this thing looks like. So I'm going to draw it as a function of t. As always with these kinds of problems, these Laplace problems, we're really only interested in positive values of t, so I don't need to worry about negative t. And we know that this thing changes at t equals to 1. Okay, so this function is behaving like t, so it's just a straight line passing through the origin between 0 and 1. So you can see that its maximum value is going to be 1. And after that point, it just takes the value 0. Okay, so we need to decide what's happening at the discontinuity. So we don't have a value here, and we don't have a value here. So in fact, notice here that there's no value defined for t is equal to 1. Now, how would I write this down as a Heaviside? Well, remember that the way we build these things up is by imagining that we're switching on and switching off functions. So taking a look at our function here, you can see that I'm going to immediately switch on the function g of t is equal to t. So I'm going to switch that on at t is equal to 0. I'm going to let that run along until I get to t is equal to 1, and then I'm going to switch it off. So how do I write switch on, switch off? Well, remember that we write that as a Heaviside, u of t minus the switch on time, minus a Heaviside, u of t minus the switch off time. And the way we read that is switch on at t is equal to 0, and switch off at t is equal to 1. Okay. What about the rest of the function? Well, the rest of the function is just 0 for the rest of eternity. So I don't actually have to include anything more in my function g of t. I've turned on t at time t is equal to 0. I've switched it off at t is equal to 1, and that's all that there is to this function. Now notice that I've got a u of t minus 0. Let's write that out again. So I've got t u of t minus u of t minus 1. And remember that for these Laplace transform problems, I'm really only interested in values of t greater than or equal to 0. So what I have here is a function u of t that's u of a positive number, right? T is always positive, so u of a positive number, and I know that that's always equal to 1. U of a positive number is always equal to 1. What about this bit here? Well, this will only be 1. This will only be take a value of 1 when its argument is positive, when t minus 1 is a positive number. And that'll only happen when t is bigger than 1. So let's now use that to write out this full expression, 1 u of t minus 1 times t. So that's my function g of t expressed using the Heaviside function. And we use this idea of switching on the function at t is equal to 0 and switching it off again at t is equal to 1 to write that in this form. Now what we're going to do is we're going to take the Laplace transform of that. But before we do that, we want to write down a useful little formula from our Laplace transform tables. And that formula is given by the Laplace transform of u of t minus c, f of t minus c, is equal to e to the minus cs big F of s, where of course big F of s is the Laplace transform of little f of t. So we recognize that as the second shifting theorem. It tells us that a shift by c and a cut at c is the same as multiplying by e to the minus c times s. And so we're going to make use of the second shifting theorem when we're finding the Laplace transform of this function g of t. To do that, I need to, however, rewrite this function so it actually looks like this form, that it has a cut and a shift. Now let's take a look at the function that we have. I have a cut at t minus 1, but I don't yet have a shift. And the reason for that is because I don't have everywhere that t appears, it appears in the form t minus 1. In other words, I don't have a function of just t minus 1. So what I need to do is to rewrite that function g of t now, so it's written in the form of a shift plus a cut. So let's try that. We've got g of t let's multiply out my expression, t minus t u of t minus 1. That first bit there, t, that doesn't bother me too much. I know what the Laplace transform of t is. It's going to be 1 over s squared. But this t times u of t minus 1, that I need to deal with a little bit more carefully. So what I'm going to do is I'm going to use a little trick here. I'm going to write t as t minus 1 plus 1. So I've just added and subtracted the same number. Obviously that doesn't change my answer. And then I'm going to pull that number 1 out. So I've got t minus 1 u of t minus 1. And I've got minus times 1 times u of t minus 1. So now you can see why I did that little adding and subtracting. It didn't change my answer, but it now is written in the form of a t minus 1 times u of t minus 1. It's written in the form now of a function that's been shifted plus a cut. Notice that I also picked up this extra bit here, u of t minus 1. That's fine again because I know what the Laplace transform of that is. Now I'm ready to find the Laplace transform of g of t. it's going to be given by the Laplace transform of t minus the Laplace transform of t minus 1 u of t minus 1. So this is where I'm going to have to use that second shifting theorem. It tells me that I just multiply by e to the minus cs, so in this case c is 1. E to the minus 1 times s, multiplied by big F of s, where big F of s is the Laplace transform of my unshifted, uncut function. So we need to figure out, looking at this expression here, what is the unshifted, uncut function. So let me write underneath this what the shift and the cut looks like. So you can see that u of t minus 1, that's the cut. F of t minus 1 is t minus 1. So that implies that f of t, without a shift, without a cut, is just t. So what's the Laplace transform of t? Well, again, it's 1 over s squared. And the last piece then is the Laplace transform of u of t minus 1. And we know that that's equal to, let's put it down here, e to the minus s, 1 over s. Let's gather together those terms. I've got 1 over s squared. I can pull out the minus e to the minus cs, and c, of course, is just 1. And I've got a 1 over s squared plus 1 over s. So that's the Laplace transform of g of t. Okay, so the next part of this question then asks us to use this idea then to find, actually we have a part C here that we need to deal with, use the partial fractions to find the inverse Laplace transform of the function. And then you see we're going to use the solutions from part B and C here to solve this differential equation. So let's take a look at part C. So we're looking for the inverse Laplace transform of 1 over s squared s plus 1. And you can probably guess that this is helping us towards solving that last part of this problem, part D. And we're also told in this question that we need to use partial fractions. So let's bring out our par frac, 1 over s squared s plus 1. So I'm going to write this as something over s squared plus something over s plus 1. Because I have that s squared on the bottom, I can't just put a over s squared. I have to put a s plus b, because I need to balance the power on the top with the power on the bottom. And I have a plus c over s plus 1. Or you could also write this as a over s plus b over s squared plus c over s plus 1. Those are actually completely equivalent ways of solving this partial fractions problem. So then we cross multiply and balance or match the numerators. So we find, if I match up the numerators, that 1 is equal to as plus b s plus 1 plus c s squared. So now we're going to make some subtle, some clever choices for s. The first one I'm going to use is let s is equal to 0. That's a nice one to use because it kills off a and it kills off c, so that leaves me with b times s plus 1, so that's just 1, is equal to 1, so that gives me b is equal to 1. What else can I do? Well, I could use s minus 1, because that would kill off this term, so killing off a and b and leaving me with c. So that gives me 0 plus c times minus 1 squared is equal to 1. So that gives me also c is equal to 1. And finally then I need to make a choice to try and figure out what a is. Now unfortunately I can't use 0, I can't use minus 1, sorry, that was supposed to be a minus 1. But I'm free to choose any other value of s that I find convenient. So let's choose s is equal to 1. So we're going to have a times s plus b, let's put in the value of b, times s plus 1, so that's 1 plus 1, plus c, again c we have, so that's 1 times 1 squared is equal to 1. So multiplying that out, I've got a plus 1 times 2 plus 1 equal to 1. You can see that those 1's are going to cancel. I'm going to get a plus 1 is equal to 0, which gives me a is equal to minus 1. So I have a, I have b, I have c, so f of s, which was given by 1 over s squared, s plus 1, which is equal to minus 1 over s, plus b over s squared, so b was 1 over s squared, plus c over s plus 1. And of course, if we've got a few extra minutes in the exam, it's always worthwhile going back and checking that we do in fact have the correct answer, just by multiplying, cross-multiplying. So let's just check it. So we've got minus 1 times the other coefficients, plus 1 times the other coefficients, plus 1 times the other coefficients, all over. We've got an s, we've got an s squared, we've got an s plus 1. So I'm going to have minus 1 times s squared times s plus 1, so that's minus s cubed minus s squared plus s squared plus s cubed, all divided by s cubed s plus 1. So let's see if there's some cancellations. The s cubeds cancel out, the s squareds cancel out. I'm left with just an s on top, and that cancels one of my s's on the bottom to give me exactly what I started off with. So that check works. All right, so now we're ready to find the inverse Laplace transform of this function big F of s, now that I've written it in terms of its partial fraction expression. So again, let's write big F of s is equal to minus 1 over s plus 1 over s squared plus 1 over s plus 1. So the inverse Laplace transform we can just use our tables for that. That's going to be minus 1 plus t plus e to the minus t. Well, those are all in your tables. All right, so let's now move on to part D of this question. And again, we're going to be using what we've found in parts B and C. So we're asked to use Laplace transforms to solve this differential equation where g of t is exactly the function in B, and we're given some additional information that the y at time t is equal to 0 is equal to 0. So this is part D. We're told that we have a differential equation y prime plus y is equal to g of t, and we're told that y at time t is equal to 0 is equal to 0. So we're going to take the Laplace transform of both sides of this equation. So the Laplace transform of the left-hand side becomes the Laplace transform of y prime. So let's let big Y of S, let's call it, equal to the Laplace transform of little y of t. So using the formula for the Laplace transform of a derivative, I'm going to get S times the Laplace transform of y minus the initial value, y at t is equal to 0, plus the Laplace transform of y. So I also have a Laplace transform of y as well. So you can see I've got y is equal to 0 at t is equal to 0, so that's going to go away. And I'm left with common factor of y of s, which I can take out, times s plus 1. And that's our left-hand side of our differential equation after I've applied the Laplace transform. What about the right-hand side? Well, this is the Laplace transform of g of t. And we found that in part B of this problem. So we can just pull that right out. It's given by 1 over s squared minus e to the minus s, 1 over s squared plus 1 over s. So let's put that together now. I've got my left-hand side was y of s plus 1 is equal to my right-hand side, which is 1 over s squared minus e to the minus s, 1 over s squared plus 1 over s. I need to rearrange this expression now to solve for big Y of s. I'm going to have dividing by s plus 1, 1 over s squared s plus 1, minus e to the minus s, 1 over s squared s plus 1. Minus e to the minus s, 1 over s plus 1. Okay. Now let's just put together those two terms that involve e to the minus s. In fact, let's take out the common factor of e to the minus s. That's a plus then. Let's see if we can put those two terms together and see if there's some cancellation. You can see that they both have this common factor of s times s plus 1. So let's put it all over s squared s plus 1. I'm going to have a 1 plus s on top, right? So I'm just pulling out s squared s plus 1, so that gives me a factor of 1 there, and I've got s squared s plus 1 s over s squared plus 1 from the second term. So you can see that there's going to be a cancellation between the s plus 1 there and the s plus 1 there. And I'm left with e to the minus s all over s squared. Okay, now I'm ready to find the inverse Laplace transform of this to solve for y of t. So inverse Laplace transform of big Y of s is going to be the inverse Laplace transform of 1 over s squared s plus 1 minus inverse Laplace transform of e to the minus s over s squared. The first term is actually what we found from part C of this problem. So we saw that that was minus 1 plus t plus e to the minus t. So that's from part C. What about the next part, L inverse, or inverse Laplace transform of e to the minus s over s squared? We actually saw that also in part B. It's a function of s multiplied by an e to the minus s. So we're going to use the second shifting theorem for that. So the e to the minus s is going to become a shift and a cut, and the 1 over s squared, the Laplace transform of that, is just t. So I take the function t, right, that's the inverse Laplace transform of 1 over s squared, and then I give it a shift of 1 and a cut at t is equal to 1. So that's using the second shifting theorem. And that's our solution then to our problem, or our differential equation. Let's now take a look at another example, example 2, that involves, again, building up a couple of different steps so we can solve a differential equation. Again, I'm going to skip part A here. It's mostly just using your table of Laplace transforms. I'm going to move right along to part B. So we're given a function g of t. It's got some expression here. We're going to express this in terms of the unit step function and then find its Laplace transform. We're going to find an inverse Laplace transform that's going to prove very useful in the final part when we put it all together to solve the differential equation. So this is question 2, part B. Again, part A is just an application of your tables, so you can do that yourselves. So in part B, we're looking at the function g of t is given by 0 for all values of t less than 1. It's given by t minus 1 for t between 1 and 2, and I'm being careful about my discontinuities there. And it's given by 1 for t greater than 2. So we want to sketch that, express it in terms of Heavisides, find its Laplace transform. So what is this thing going to look like? As always, I'm not really interested in what's going on for negative t, so let's just look at values of t greater than 0. I've got t 1, 2, 3, 4, and so on. So between t is equal to 0 and 1, this function is simply 0. For values of t between 1 and 2, I'm told that this is equal to t minus 1. So it's got a slope of 1, positive slope, but it's been shifted so that its intercept is at y is equal to minus 1. So what that means is that this is actually going to be a function that increases at t is equal to 1, it's equal to 0, and then increases to a value of 1 at t is equal to 2. And then after that, it just takes the value it just takes the value 1. So you can see that this is a lovely continuous function. It changes suddenly, but it has no jumps. So this is our function g of t. So let's find what this function looks like when I express it in terms of its Heaviside. In terms of Heaviside functions. And again, I'm going to use this idea of switching on and switching off different functions. The first thing I'm going to switch on is at t is equal to 1, I'm going to switch on the function t minus 1. But then I'm going to switch that off at t is equal to 2. So take the function t minus 1, switch it on at t is equal to 1, and then switch it off again at t is equal to 2. Now, I'm not done yet because I still have a function value after values of t is equal to 2. So I can't just leave it like that. I also have to take the function 1 and switch it on at t is equal to 2. So this is a switch on, switch off, followed by a switch on, and then we'll leave it on. Now if I hadn't included that point there, my function would have dropped right back down to 0 and continued at 0 for the rest of eternity, so we don't want that. Okay, so let's multiply this out a little bit, and bear in mind that, just like in the last problem, we're going to be using the second shifting theorem, which means that all of my functions here, I want them to appear in the form of a shift plus a cut. You notice that I have two terms here in terms of u of t minus 2. Let's put those two things together. I've got t minus 1. I can take that other term inside and I'll get t minus 2. U of t minus 2. And if we look at that expression there, you see that t minus 1, u of t minus 1, so that's a shift and a cut at t is equal to 1. T minus 2, it's a shift and a cut at t is equal to 2. So this is already in the form that I need it to use the second shifting theorem. So the second shifting theorem then is a straightforward application of that idea that every time I have a function that's written as a shift and a cut, I simply get something that's e to the minus times the shift times s multiplied by the Laplace transform of the unshifted uncut function. So the uncut function means we remove the heavy side, remove the shift, we're left with just little old lonely t. So the Laplace transform of t is 1 over s squared. Again, I've got u of t minus 2, u of t minus 2. So I've got e to the minus shift times s times the Laplace transform of the unshifted uncut function. Remove the cut, remove the shift, I'm just left with t. So the Laplace transform of t is 1 over s squared. So tidying that up a little bit, I've got e to the minus s over s squared minus e to the minus 2s over s squared. Okay, so that's the Laplace transform of my function g of t. Let's take a look now at part C of this problem. So in this part, we're given some complicated looking rational polynomial, and we're going to find its inverse Laplace transform using our various tricks that we have for doing that. So we saw that there's really only two possibilities in these kinds of rational polynomials. Either we have a function that can be, its denominator can be factorized, or we have something that we need to complete the squares. So let's take a look. F of s is equal to s plus 2 all over s plus 3, s squared plus 6s plus 10. So the first question we need to ask is, this denominator here, does it factorize into s plus something times s plus something, or do we need to complete the squares? So this doesn't have real factors. You can try that yourself. You can either use the quadratic formula or you can stare at it for a while. Instead, we're going to complete the squares. It doesn't have factors, so this is what we need to do instead. So I'm going to do this as follows. I'm going to let s squared plus 6s plus 10 equal to some s plus a squared plus b. And if you multiply that out, you'll see that this becomes s squared plus 2as plus a squared plus b. So we can match the corresponding terms on left and right here. So 6s has got to be equal to 2as, and 10 has got to be a squared plus b. So matching 6s is equal to 2as immediately gives us that a is equal to 3. And matching 10 is equal to a squared plus b. A is equal to 3, so that's 9 plus b. We see that b is equal to 1. So we've completed the squares. We found that s squared plus 6s plus 10 is equal to s plus a all squared plus b. And you can always check that if you multiply that out, just to make sure that you found the correct completion of the squares. So I get s squared plus 2 times 3 times s plus 3 squared plus 1, which is indeed s squared plus 6s plus 10. So that is the correct square. Okay, so we found that denominator in terms of its completed square. So let's write out what we get in that case. So s plus 2 all over s plus 3 squared plus 1. Now remember that when we're going to be inverse Laplace transforming this thing, it has on the bottom something of the form of s plus 3 all squared. So that kind of looks like it's a shift, right? It looks like a shifted version of s squared. But we don't have a corresponding shift on the top. So I need to fix that by, again, using my little trick of adding and subtracting 1. Why would I do that? Well, you can see that that's then going to give me something like s plus 2 plus 1, so that's s plus 3. And I can take that minus 1 and form a new fraction. So again, all I did there was add and subtract 1, so that I have an expression here that has s plus 3 on top and s plus 3 on the bottom. And I have an expression here which doesn't have any s's on the top, but it has s plus 3 on the bottom. So everywhere that s appears, it appears in the form s plus 3. It has a shift everywhere. So now I can use my Laplace transforms. So this is the first shifting theorem, the inverse Laplace transform of a shifted function of s is going to be e to the minus a times t times the function f of t, where f of t is the inverse Laplace transform of the unshifted function f of s. Okay, so this is our first shifting theorem. You can see that I have a function here that's been shifted by 3. I have a function here that's been shifted by 3. So in each of these cases, I'm going to end up with e to the minus 3 times t. But then I need to figure out what f of t is going to be. I need to figure out what the unshifted functions are. So let's take a look. If I remove the shift here, I'm going to get s over s squared plus 1, and I'm going to get 1 over s squared plus 1. So in both of these cases here, we've got a sine and a cosine, right? So I've got that f of t, or let's write it like this, the inverse Laplace transform of f of s, again using the first shifting theorem, e to the minus 3t, times the inverse Laplace transform of the unshifted version of this, s over s squared plus 1. Well, that's simply cosine of t. Minus first shifting theorem, e to the minus 3t, times the inverse Laplace transform of the unshifted version of this, 1 over s squared plus 1. And that's the sine of t. So there's the inverse Laplace transform of f of s, where we've made use of completing the squares, the first shifting theorem, and the inverse Laplace transforms of s over s squared plus 1 and 1 over s squared plus 1. Finally, now we're ready for part D, which is going to put all this together. So in part D, we're asked to use Laplace transforms to solve this differential equation. And we're going to sketch that. So we may end up using part C or part A. I don't think we actually use part B. So let's see what happens. Okay, so we've got part D. Here's our differential equation. Y double dash plus y is equal to u of t minus 2 pi. And we're going to take the Laplace transform of each side of this equation here. We're also given some initial conditions. Those are that t is equal to 0, y is equal to 1, and y prime is equal to 0. So we're going to take the Laplace transform of each side of this equation. So the left-hand side, I need the Laplace transform of y double dash plus y. So we know that the Laplace transform of y double dash is going to be equal to s squared times the Laplace transform of y minus s times the initial value of y prime minus initial value of y. So that's there. That is my Laplace transform of y double dash. And I need to add the Laplace transform of y as well, so that's just y of s. I can use my initial conditions now, so y at 0 is equal to 1, y prime at 0 is equal to 0. I can pull out the common factor of y of s, and that's what I'm left with. What about the right-hand side? I have the Laplace transform of u of t minus 2 pi. Well, that's one of our tabled Laplace transforms. That's just going to be e to the minus 2 pi s all over s. So let's match each of those sides. So I've got y of s squared plus 1 minus s on the left-hand side is equal to e to the minus 2 pi s all over s on the right-hand side. So y of s is equal to, let's bring the s over to the right-hand side. So I get s divided by s squared plus 1 plus e to the minus 2 pi s e to the minus 2 pi s 1 over s times s squared plus 1. Okay, so we're going to look for the inverse Laplace transform of this expression here. The first one is fairly straightforward. That's just going to give me a cosine. The second one involves an e to the minus 2 pi s times some complicated looking function. So I want to take that complicated looking function and use partial fractions to simplify it. So let's look at 1 over s times s squared plus 1 and write that as a over s plus something over s squared plus 1. Now you notice that I've got an s squared plus 1 on the bottom there, which means I have to compensate by having a bs plus c on the top so that it all balances out. Cross multiplying, and equating the numerators gives me a times s squared plus 1 plus bs squared plus cs. So again, now I can choose convenient values for s to solve for a, b, and c. So let's let s equals to 0, which gives me 1 equal to a times 1 plus 0. So that tells me that a is equal to 1. And now I'm actually in a bit of a pickle because I need to find other values of s to find b and c, but s is equal to 0 isn't going to work. And there's no convenient value I can plug in here to cancel that factor out. So why don't I multiply this expression out? So I get 1 equal to, a is equal to 1, so s squared plus 1 plus bs squared plus cs. You can see that those factors of 1 will cancel out. So I get the following expression. I get bs squared plus cs plus s squared is equal to 0. So I have there one equation involving b, c, and s. And I want to find b and c, so I want to find two equations for two unknowns. So I'm going to choose two different values of s. Let's try s is equal to 1. There's no particular reason I'm choosing that value. It's just a simple value. So b times 1 squared plus c times 1 plus 1 is equal to 0. That's my first equation. Let's try s is equal to minus 1. I've got b times minus 1 squared plus c times minus 1 plus 1 is equal to 0. So these are two equations for two unknowns. You can see that I can solve them simultaneously. Right away I could just add them together to cancel the c's. So that would give me 2b plus 2 is equal to 0, which gives me b is equal to minus 1. And I can go back now and find c is equal to minus 1 minus b, which is minus 1, plus 1, which is 0. So that gives me all of the pieces I need. I have now that 1 over s squared s plus 1. Sorry, 1 over s squared plus 1 is given by a over s plus bs over s squared. So a was 1. So that's 1 over s plus minus 1 times s over s squared plus 1. And it's always worthwhile just checking to make sure we haven't made a mistake. So I get s, let's see, cross multiplying here, I'm going to get 1 times s squared plus 1 minus s times s all over s squared plus 1. The s's cancel out. I'm left with 1 over s squared plus 1. So indeed that works out. Okay, so I found my partial fractions expression for that. Now let's find the inverse Laplace transform of e to the minus 2 pi s times that thing. So it's worthwhile writing out again what big Y of s is. Big Y of s was equal to s over s squared plus 1 plus e to the minus 2 pi s times what we've just found. So 1 over s minus s over s squared plus 1. So I'm going to use the second shifting theorem for these pieces. So y of t, first one is going to just be cosine of t. That's fairly straightforward. Second shifting theorem tells me that if I have a multiplication by e to the minus 2 pi s, that's going to turn into a shift and a cut. So let's first of all figure out what the Laplace transforms of each of these pieces are. The Laplace transform of 1 over s is just going to be a constant. It's just going to be equal to 1. And the Laplace transform of s over s squared plus 1, well again that's going to be cosine of t. So I'm going to take my constant and my cosine of t and shift them and multiply them by a cut. So let's first of all multiply them by the right cut. So I've got u of t minus 2 pi, that's a cut at t is equal to 2 pi. And then I'm going to multiply that by a shifted version of the Laplace transform of 1 over s. The Laplace transform of 1 over s is just a constant. A shift of that is just the same number, 1. What about the second term, s over s squared plus 1? The Laplace transform of that is cosine of t, so a shifted version of that will be cosine of t minus 2 pi. Okay, so how would I sketch what this looks like? Well, you can see that the first part of this function is just going to look exactly like cosine of t. So let's try and write what this looks like before t is equal to 2 pi and after t is equal to 2 pi. So for t less than 2 pi, I'm just going to have my function is cosine of t. So that's t is less than or equal to 2 pi. Afterwards, I'm going to have cosine of t, and this bit is now going to be switched on, so I'm going to have plus 1 minus cosine of t minus 2 pi. And so that's for t greater than 2 pi. But cosine of 2 pi is just equal, cosine of t minus 2 pi is just cosine of t shifted over by 2 pi. But cosine has this periodicity of 2 pi. So shifting over by 2 pi doesn't do anything. So this is actually equal to cosine of t. So you can see that I'm actually going to get cancellation between this term and this term, which leaves me with a very simple expression. It leaves me with cosine of t for t less than or equal to 2 pi, and it's equal to 1 for t greater than 2 pi. So this makes it very easy to sketch what this function looks like. For values of t that are positive, I've got 2 pi, pi, 3 pi. Cosine is bopping around between 1 and minus 1. Up until t is equal to 2 pi, this thing is just going to look exactly like cosine, so we know what cosine looks like. It does something like this. But then at t is equal to 2 pi, my function changes and just becomes equal to the constant value 1. So you notice there's no discontinuity, but it just stops oscillating like cosine and becomes a constant value. So this was another example of a problem where I needed to use various shifting theorems and various tricks and partial fractions, completing the squares and so on, to solve a differential equation using Laplace transforms.